afternoon's meeting, the final meeting of this session of the Computer Conservation Society. For those of you who don't know me, I'm Roger Johnson. I'm not the chairman of the CCS, that's Rachel Burnett. Rachel sends her apologies and hopes to be joining us during the afternoon. She had a business meeting this morning, which is normally held in London, but she doesn't determine where it was held, and those who do decided to hold it in Milton Keynes. So I think at the moment she's probably coming back at high speed with Virgin trains to Euston. So she's hoping to join us. Anyway, to this afternoon's business, this is the second talk this session on the work of Alan Turing, and it's an enormous pleasure to welcome Professor Brian Carpenter to the meeting. Brian's just retired as Professor of Computer Science at the University of Auckland, and before that he'd worked for IBM and for CERN and also for Massey University in New Zealand. The title of Brian's talk this afternoon is Alan Turing, Computer Designer, and I think this will provide an interesting and complementary talk to the one we had 2 months ago on Alan Turing and his influence on his British contemporaries. So, Brian, can I, without further ado, welcome you to the CCS and to invite you to address the topic. Thank you.
Thank you very much. We may need a sound check. Can someone at the back hear me?
Yep.
Yes. Yep. Okay, good. So, I should mention that a colleague of mine in Auckland, Bob Doran, and I have been working on this topic on and off since 1975, more off than on, but we've collaborated on at least 3 occasions on analysing Turing's work. And he gave a lecture in Auckland, not with the same slides, not with exactly the same material, but on the same general theme, yesterday, UK time, the day before yesterday, New Zealand time. Okay, well, you've seen that. So, the thing about Turing is that he's usually thought of as a theoretician. He was a B-star wrangler, the same year as Maurice Wilkes in Cambridge. Yes, he was. I looked it up.
Maurice had bigger marks.
That may well be true.
So he told.
I can believe that. In 1937, he wrote, "It's possible to invent a single machine which can be used to compute any computable sequence. If this machine U is supplied with the tape on the beginning of which is written a string of quintuples separated by semicolons of some computing machine M, then U will compute the same sequence as M." So that's a really theoretical statement. So how did it come about? By the end of 1945, as you probably already know, he wrote a document called Proposals for Development in the Mathematics Division of an Automatic Computing Engine. I think that's sort of an interesting jump between theory and practice. Let's read that sentence again. It uses the word invent, it uses the word machine, it uses the word tape. It's written machine. Okay. In other words, the founding statement of computability theory was basically written in physical terms. It wasn't written in mathematical terms. I think that tells you something about the way he thought. What would it take to build that machine? A tape on which you can write, read, and erase symbols. Well, Coulson demonstrated magnetic wire recording in 1898, so that was around in 1937. You need to be able to store symbols and perform simple logic. Well, Eccles and Jordan patented the flip-flop, what they called it the multifibrator trigger, in 1919. And Rossi, who was a physicist, invented the coincidence circuit, what we would now call an AND gate, in 1930. So, in my opinion, you could have built U in 1937, and not even a mechanical U, but an electronic U, and it would only have been slightly more bizarre than building a differential analyzer with Meccano, which I'm sure you all know was a popular pastime in those days. So there's the evidence for the 3 statements I just made. That's the Rossi circuit. his work's been analysed. There's a recent publication in the American Journal of Physics analysing Ross's work, including his original circuit diagram. That was easier than looking for the original publication. That's the Eccles-Jordan circuit according to British Patent 148582, which you can find from the usual sources of patents. And that's the Poulsen telegraphone wire recorder. You can sort of see the drum here on which the wire is wrapped. You can't make out much in the way of detail. And he didn't actually invent the concept, by the way. Someone else whose name I forget actually proposed the concept of wire recording, and Poulsen actually made one and sold it. So this was real technology in 1937. About 1960, a fellow called Gisbert Hasenjäger built a slightly modified universal Turing machine. That's the thing at the top. If you want to see that, you need to hurry to Cambridge, find the Isaac Newton Institute of Mathematics, and they have that machine on display at the moment in their lobby. And I attended a talk on that a couple of weeks ago in which the speaker showed a video of the machine actually working. There have been more recent attempts to build Turing machines. This is the Lego of Doom. It's quite clever because the tape is actually a track, because Lego apparently includes a railway track, so that's what they use as the tape. And then the machine walks along the track instead of the tape running through the machine. And there's a fellow called Mike Davey who built this machine, which really does print zeros and ones on a paper tape and has a mechanism for erasing them from a paper tape. And again, you can find video of this thing working with the Google. So Turing machines, even when they were invented as the foundation of computability theory, were not unrealistic thought experiments. Much more realistic than Maxwell's demon, for example, which is probably the most famous thought experiment. Maxwell's demon would be quite hard to construct. Turing was actually a pragmatist, and that's, puts the lie to the idea that he was just a theoretician. In 1937, he suggested adapting an analog tide prediction machine to search for the zeros of the Riemann zeta function. By mid-1939, he'd got a £40 grant to build it, and his room was reported to be cluttered with high-precision gear wheels as a result. And of course, he was very well aware of Babbage and his failed attempts to build a machine. Also in 1937, he designed and partly constructed an electric multiplier. So these were the same year as the Turing machine theoretical paper was published. And in 1940, the other pragmatic thing he did, which is fairly well known, of course, my source for a lot of this is Andrew Hodges' book, obviously. He decided to protect his assets against invasion by burying 2 silver ingots, which is, in my mind, a pretty pragmatic thing to do. And he could never find them again, so, I think there are probably still people who would like to go and find them. They're worth quite a bit by now. So he was a pragmatist. That's still not a computer designer. So I assume everybody in this room knows what the top picture is. The bottom one is also near Milton Keynes. I found it on the Milton Keynes Heritage website, which, for the popular image of Milton Keynes, is a very strange idea that it's a Milton Keynes Heritage website, but there is. That's Hanslope Park, photographed just after the war. It's quite interesting because you can make out, probably not from the back of the room, but you can make out the radio masts and the huts, which are very similar to the huts you find at Bletchley Park. Because of course Hanslope Park was used for secret R&D during the war, just like Bletchley Park. These days it's used for keeping secret records really secret, apparently. So secret that the government can't find them. From late 1943, Turing moved from his central role at Bletchley Park to Hanslope Park, which was doing radio research not very far away. His work there was on a speech encryption device, which he did with one assistant and a few square feet of bench space. But the fact of the matter is, for 2 years, he gained practical experience as an amateur electronics engineer and wielding his own soldering iron. He knew the theory of circuits, and he could calculate and predict how circuits would behave. And so he basically became an electronics engineer of sorts. Probably not many engineers would recognize him as an engineer, but I'm sure he thought of himself as an engineer as well. Oh, and a bit later he became a management consultant. At Bletchley Park, he saw what was needed for managing a data-intensive operation. So, quote from, not from the ACE report, but from his lecture to the London Mathematical Society a couple of years later. One of our difficulties will be the maintenance of an appropriate discipline so that we do not lose track of what we are doing. We shall need a number of efficient librarian types to keep us in order. I have already mentioned that ACE will do the work of about 10,000 computers, which of course meant 10,000 human computers. So he knew that managing computing centers was going to be an issue. He also foresaw what systems programmers would be like with their mystique and gibberish. I love this quotation. This is also from the 1947 lecture. The masters, that's the masters of the machine, i.e. the programmers, are liable to get replaced because as soon as any technique becomes at all stereotyped, it becomes possible to devise a system of instruction tables which will enable the electronic computer to do it for itself. So he figured out that once you knew how to do something, you could program it and make the person who had previously been doing it redundant. And I note the fact that by 1947 he was calling it the electronic computer, completely modern terminology. It may happen, however, that the masters will refuse to do this. They may be unwilling to let their jobs be stolen from them in this way. In that case, they would surround the whole of their work with mystery and make excuses rather than well-chosen gibberish whenever any dangerous suggestions were made. Okay, just read the README file, which comes with any Linux utility, and you will see that his words have come true. So I think it shows that he was far from a theoretician. He knew how the real world worked. He knew how to build electronics in an amateur sort of way. And he knew how people reacted. So people talk about whether he was autistic or at least had Asperger's syndrome. I'm not convinced when I read this quote, because his prediction of how human society and humans would react to this technology was remarkably accurate. And this was written in 1947, remember? Even the Manchester machine hadn't run when this was written. He was also a sociologist. In other words, by the mid-1940s, he had a pretty good feel for the sociology of computing centers as they existed for the following 50 years. See, that style of big box computer centers is just about faded away now, but 50 years of that situation existed. He did not foresee that those centers would disaggregate because of the network. He didn't foresee the sloppy trial and error programming which is caused by cheap interactive workstations. You know, there was a time in my life when compiling a program was a sufficiently painful and expensive operation that you tried to make it right first time. I don't think any programmer today tries to make something right first time. My guess is that he would not have found did you try switching it off and on again very funny, because that was exactly the opposite of how we thought things should be done. Okay, in late 1944, the National Physical Laboratory approved the creation of the Mathematics Division. Okay, after the invasion of Europe, but before the war was over. So this was already forward thinking about what was needed after the war. The support came from the Ministry of Supply, came from Commander Edward Travis, who was the boss of GCCS, Hartree, of course, and L.J. Comrie, the New Zealander who founded the Scientific Computing Services Limited in 1938 when he got thrown out of the Royal Greenwich Observatory or somewhere like that. So not being politically correct. SCS Limited, by the way, is still registered at Company's House as a private company. I happen to know who owns the company now. I don't want to breach his privacy by naming him. What he did fairly recently was sell the domain name scs.co.uk to a furniture company. But until a few years ago, scs.co.uk was the Scientific Computing Service Limited, founded by Comrie in 1938. So this division of NPL was set up to provide and coordinate national facilities for the automated computation, including military applications. The first head was J.R. Womersley, better known for his later work on fluid dynamics, because he's got an equation named after him, after he left NPL. But he'd read on computable numbers before the war. He knew all about Turing's theoretical ideas. In early 1945, before he took up his job at NPL, he went to the US, learned about ENIAC, and learned about plans for EDVAC. So he knew what was believed to be possible in the area of automated computation. Of course, automated computation did not automatically mean electronic digital computers in 1944 or 45. It might have meant computers made out of Meccano or analog machines of some other kind. That's Womersley Comrie, pretending to be a computer. You know, the reality is that in those days, most of the people operating such machines were women. But I'm sure that Comrie knew how to operate one. Turing, the civil servant. As the war neared its end, he was no longer playing a major role in cryptography. He moved across to work on speech encryption at Hounslow Park, and that was a fairly low-profile project. In June 1945, he was visited by Womersley from NPL and was shown von Neumann's first draft of a report on the EDVAC. He accepted a job at NPL and went to work there the 1st of October. So civil servants behaving creatively. Womersley was a sort of strange character. Not very much is known about him. He changed careers several times, which is how he comes to be remembered for an equation, not for being Turing's boss. During the war, he worked on statistics, and before the war, he worked in Manchester with Hartree on the differential analyzer that was at the Shirley Institute in Manchester. He created a one-man section of his division, which consisted of Turing, to study the design of an automatic computing engine. And the result was, by the end of 1945, Turing had written this document called Proposals for Development in the Mathematics Division of an Automatic Computing Engine, ACE. It was presented to the Executive Committee of the NPL in March 1946. And it was supported by Womersley, of course, and by Hartree, who I guess was an advisor to the NPL or something like that. The committee did approve the project. They didn't approve the design in the report as such. They approved the project. Incidentally, if you don't know, the chairman of the committee was the director of NPL, Charles Darwin, who was the grandson of Charles Darwin. Though this Charles Darwin had actually trained as a physicist at the Cavendish lab in Cambridge. You know, the fact that Turing was also a Cambridge man probably came in handy, because that's how these things go. Okay, incidentally, ACE is probably the #1 TLA. TLA, if you don't know, means three-letter acronym. It's probably the first one in electronic computing, and in my opinion, it's the best ever. ABC was attached to the Atlas Berry computer, but that was attached retrospectively. That's not what they called it at the time. Yeah. And it was an abbreviation as well, so it wasn't actually an acronym. You're right, sir. We have pedants in the room. But regardless of that, I still think ACE is the best acronym ever. So, out of confusion, well, what confusion? In 1945, the word computer meant a human. There were lots of little analog devices, many of them mechanical. For example, bomb aiming and gun laying throughout World War II was done by small mechanical analog computers. There were a handful of semi-automatic digital computing machines, relay machines and some electronic machines, but they were expensive, awkward to use, and they were little known because of the wartime secrecy. A few people had read the EDVAC report, including Turing, as I said, but it was incomplete. If you took the EDVAC report and a box of parts and a soldering iron, you would not get a computer because it was not a completely specified design. But nevertheless, the EDVAC report contained thinking from Atanasov, Eckert and Womersley, thinking sort of co-opted by von Neumann, who put it all together. And that's how that thinking crossed the Atlantic, there's no doubt about it. The pioneering work by Zuse was completely unknown outside Germany at that time for fairly obvious reasons. So although it would be nice if Zuse was part of the story, he isn't really. Out of that confusion came enlightenment. There's 48 pages in Turing's report. He synthesized the concept of a stored program universal computer, floating point library, artificial intelligence, little details like having a hardware bootstrap loader. Of course, he didn't call it any of those 3 words. He had one, and lots of other stuff. I first read this report when it was 30 odd years old, and I was blown away. It was just so surprising and fresh. And I reread it now when it's 60 years old, and it's a remarkable piece of work. It really is. Just out of curiosity, how many people have actually read the Turing ACE report? Oh, Martin does. Simon. Okay, good. This is good, so I can tell you what's in it. You won't be bored. So there's a contents page, part 1, in its original form. Don't worry about reading this. I've got a readable version in a few seconds. And part 2 of the contents. So transcribing that into something legible. Introduction, composition of the calculator. This was the terminology he used. Storages, pluralized. Arithmetical considerations, circuit elements, logical control, external organs, that's I/O, scope of the machine, checking, timetable costs, nature of the work, etc. So there's a bit of a disdain for practicalities and the etc. Details of logical control, detailed description of the arithmetic part, examples of instruction tables, design of the delay lines, design of the valve elements, and alternative forms of storage, because he chose delay line storage, but he discussed the alternatives. So there's a lot of meat in there. It's not just generalities, and it's not just logical design. So this is the kind of drawing that he used for the logic circuits. This notation is directly derived from the notation in the famous paper by McCulloch and Pitts, A Logical Calculus of the Ideas Immanent in Nervous Activity, published in 1943, during the war, interestingly enough. So that was the first paper that started to analyze brains, if you like, as cybernetic type of activities. And one of the papers that McCulloch and Pitts cited was Turing's on computable numbers. So there's a direct line there from his universal machine paper, the first analysis of neural activity using logical circuit diagrams, and his computer design. Drawings of logical subsystems, you can't possibly read this even from the front row, let alone from the back, but just to illustrate that he didn't just design little bits, he's got many pages of this level of detailed logical design. Zoomed in a bit on one of those, just for example, this diagram is what's called the true arithmetic operations. The 2 in a circle is an AND gate because you need 2 inputs to get 1 output. DL32 is a 32-bit delay line. It's what he also called a minor cycle, or elsewhere in the document he calls that a word. So the contents of a 32-bit delay line he calls a word. And you really have to study this in detail to understand what's going on. I just wanted to give you a flavour of it, because here he shows 1 delay line here, another delay line here, 2 AND gates, a 3rd AND gate, I think that means multiplexer, and the outputs go off further on in the diagram. So if you want to drive yourself crazy, you can try and figure out how it all works. Then for the individual logic elements, he gave valve-based circuit diagrams with resistors and voltages and all the usual things you would find in circuit diagrams in the 1940s and 1950s. And specified the valve type, that's a 6SN7, famous double triad. That's a 6537, I think. Oh, yes, sorry, you're right, I'm stupid, my brain is gone. I played with these things as a teenager. because they used to get them scrap value.
In practice, the double triode only had one cathode. The one in rectifier had one cathode and then separate parts thereon, two separate ways.
Yeah. But logically, it had to. I think that's, he was a logician as well. But in any case, yeah, I mean, the point is, this is not a circuit diagram that you would have found difficult to build, right? Obviously.
It's ranging on it, yes.
Yeah.
You don't have two models there.
Yeah. So, let's go a bit more detail. He gives an outline of the principles of stored program computers, what is binary representation, and what is floating point arithmetic. He gives a detailed architecture and instruction set. He gives detailed logic diagrams and circuits. He gives example programs, and he said it would cost £11,200, which to scale it was about 20 times his salary. Probably he was a senior scientific officer, I would think. So 20 times his SSO salary in 1945. That estimate, of course, was ridiculously low, but that started a long tradition in IT. So he was a forerunner also in the budget business. It would have been a serial machine. This design, written in 1945, of course, was not a machine that was ever built. It would have been a serial machine, 1 megahertz with 32-bit words. If you're charitable, that works out at about 0.03 of a bit. And using Word in that usage, as far as Bob Doran and I have been able to determine, came for the first time in that report. Von Neumann did not use the word Word to describe computer words, and nobody else did in anything that we found earlier than the Turing report. It had 32 registers. He didn't call them registers, he called them temporary storage, or TS, and they were 32-bit Mercury delay lines. And here's the novelty, or one of the novelties: it had a register-to-register instruction set. Okay, whereas EDVAC, which was the design that von Neumann had sent over the Atlantic, was of course an accumulating machine. And the other thing about ACE is that as designed it only had 11 instructions, very economical instructions. The logical overview from the ACE report. These things here, there's 32 registers, TS1 to TS32. Up at the top, there's in his design 1,024 long delay lines. They were just by coincidence delay lines that contained 1,024 bits each. So that would have been a megabit of memory, which probably seemed like a lot at the time. There's a common out bus and a common in bus. So all these registers and memory units can talk to each other through a common bus, which is a serial bus, remember. And over here on the right, there's a thing called CD and a thing called CI. Go a bit more into that on the next slide. It's just a slightly blown up version of the same thing. The stuff at the top is the main memory, stuff at the bottom are the CPU registers, 32 of them. CI is the instruction register, and CD, which he called current data, was actually the instruction counter. It was the address of the instruction in the instruction register. And you'll notice that there's a loop from the output of CD to the input of CD with a +2 on it. That means once every machine cycle, we spin the value around, so CD is copied back into CD, but on the way around you add 2 to it. You don't have 1 to it. So instruction addresses go up in 2s. What's that about? In delay line memory, there's no random access. Word n+1 pops out of the memory immediately after word n, which I believe in modern terminology is called a royal pita. Think about it. That leaves no time for instruction n to complete before instruction n+1 appears. You've just decoded the last bit of instruction n, and instruction n+1 has arrived. Turing's solution was to increment the instruction counter by 2, which in practice gave you time to complete an instruction before the next one is due, because there was an extra memory cycle inserted which wouldn't be used before the +2 value came out of the and then went to the delay line. That avoided having to wait for a complete major cycle of the delay line for the next instruction. If you didn't do that, each time you executed an instruction, you then have to wait till one of these 1024-bit delay lines went all the way around, and then you get the next instruction, all the way around minus 32 bits, and then you get the next instruction. So that was how Turing solved that problem, by effectively interleaving instructions, so you get instructions 1, 3, 5, 7, 2, 4, 6, 8, all interleaved.
Not necessarily. They could be further apart.
Well, in the original design they couldn't, but
When I got there.
right. But of course, the way he describes it, Bob, Tor and I decided, meant that he was thinking of it as address mapping. He was saying we're mapping one half of the delay line to here and the other half of the delay line to here. So we're crediting him with thinking of address mapping. But of course, as the ACE design evolved, this became less and less viable because it became clear that there would be some instructions that would not actually complete within one minor cycle anyway, so this trick wouldn't work, so you'd still have to wait a major cycle. And they went to solution to plan B, which was the infamous optimum coding, where the program had to calculate when the next instruction would come around. You may know more about the versions than I do, but I know that somewhere between version 1 and version 7, they switched entirely to the optimum coding approach.
No, I only knew the final one that wasn't part of ACE.
Yeah. And Turing did have that idea in his head. There's a trace of it, I think, in the ACE report, and it's certainly known that that change to away from the interleaving happened before he left NGL. So let's talk about software, the way he proposed it. Remember, we're still talking about what was written in 1945. He described possible applications. The number one application was numerical analysis, which was what NPL thought they were getting a machine for. And counting butchers. One of his examples were counting butchers due to be released from the British Army in a certain week, so that presumably some other ministry, the Ministry of Butchers, could figure out how many butchers it was going to get that week. He was very contemptuous of that sort of application, which is traditionally done by Hollerith card machines at that time. He said that's not really a fit use for an electronic computer. Of course, it turned out to be the major use for electronic computers, moral equivalent to counting butchers. Once insurance companies and the like discovered they could use computers to analyze stuff. Solving jigsaws and other logical problems, which was partly a sort of symptom of Turing's slightly playful nature and partly a way obscurely of referencing logical applications like cryptography, which he absolutely wasn't allowed to mention. And playing chess, which certainly NPL didn't expect to be told they were building a machine playing chess. But that's one of the applications he suggested. And we know, of course, that during the war he discussed machine chess with Shannon in the US, and undoubtedly both Shannon and Turing ended the war thinking quite seriously about machines that could play chess and do other intelligent things. The way the coding system is described clearly foresees relocatable code, and he defines something called popular format, which is very much like assembly language. Instead of having to write your program out purely as a sequence of numbers, he provided a notation in which you could write it out in a somewhat symbolic form, which 10 years later you would clearly call an assembly language. Most surprisingly, he actually foresaw a subroutine library, including a stack for nested subroutine calls. So here is basic subroutines. So this was what he thought was the very fundamental library you would need. This is not the way he wrote it. This is the way Bob Dorr and I transcribed it when we wrote our first paper on this topic in about 1975. So there's a routine called indexing, which says, take the contents of the address contained in register 27 and put those contents in register 28. In other words, that's an indirect load. But they didn't have that terminology, obviously, in 1945. There's this thingy called discrim, which basically effectively said if register 8 is 0, then put the contents of register 16 into 24, and if not, put the contents of register 15 into 24. And so on. The interesting ones perhaps are bury and unbury. If you go through those, end with a go-to, right? Go-to statement was not considered harmful in 1945. That is basically a subroutine call, but it stacks the return address and unbury unstacks the return address. So it turns out you can build nested subroutine calls with that. You can actually build recursive subroutine calls with that. Pretty good for 1945. Then he's got a multiply routine, a double length multiply and double length add, because the machine was single length arithmetic. You could do that and define double length. I'm not even sure offhand if those weren't meant to be floating point. I've just lost power, so the screen was a little bit dull. Okay, no. So I don't know, just sort of double down. Oh, it's come back. Okay. I just was concerned the computer was about to go to sleep or something. And he's got an I/O routine called bindeck, which would convert the content of 2 registers into a card image in a particular delay line, so you could punch a card. So these are all subroutines that he defined, and he wrote a program. This is one of the example programs, CalPol, which is a polynomial calculation. And this is written in his popular form, where you see symbolic names and addresses, and you see calls to subroutines. He even used B for, I don't know if it meant branch or what, but effectively it was a branch to bury, and so on. There are bugs in that program. If you want to see an analysis of the program and find the bugs, then we published them in 1977. I'm showing you that not so that you can study it in detail and understand it, but just to realize the extent to which he was actually writing software for this machine in late 1945. So, again, this is something we did in 1975 and published in 1977. We went through this report trying to find what we thought were significant formative ideas that Turing had on paper. The first few have asterisks because they were definitely in the EDVAC report. And one thing we haven't done that we should have done is go through the material that's now known about Colossus, which wasn't known at all in 1975, and seen how many of these ideas could also be found in Colossus. If somebody wants a project, there it is. Binary implementation using standardized logic elements, that was clearly an idea that crossed the Atlantic. A complete notation for the circuits, that wasn't original. This architecture with memory, control, arithmetic unit, and I/O, which is a classical von Neumann architecture, was there, except, as I said, this is a register machine and the von Neumann architecture was an accumulator machine. Stored program is there, of course, and there are examples in Turing's work where he's already using self-modifying code, so you clearly understood the implications of stored program. Conditional branch instructions, which were fairly clumsy in ACE and were fairly clumsy in EDVAC. This address mapping idea, primitive, but it was there. Clear distinction between the instruction address register and the instruction register. That was absolutely not clear in the EDVAC report, although of course they had to invent it before they built EDVAC. It wasn't in the report. Multiple fast registers in the CPU, that was definitely original to Turing's design, and this whole business of register to register instructions was original to Turing's design. He had something we thought was very close to microcode, because it was very small instruction set, but some of the instructions had bits you could flip on that made them do different things, exactly like microcode. And the architect, I don't know why we made this into a single item. I guess it follows from the microcoding aspect. The architecture of the logic control was quite hierarchical in the way it was designed. He had whole card I/O operations, which were not discussed in the EDVAC report. Not quite direct memory access, but very, very close. There was a complete set of arithmetic, logical, and rotate orders. Arithmetic, of course, everybody had, but including logical and rotate instructions was new in ACE. It was almost certainly because of the cryptography, the cryptanalysis applications. There were built-in error detection and margin tests. That was a chapter in the report. That you needed to do this. Floating point arithmetic was in there as a design feature, not hardware floating point arithmetic, software floating point arithmetic. And the hardware bootstrap loader, or initial program load if you worked for IBM at one time. He had realized there was a problem of starting this thing up from cold, so he put in some provisions, which he didn't call bootstrap, of course. The subroutine stack, as I've discussed, very clearly understood modular programming and the need for a subroutine library. Understood the need for documentation standards, that was discussed, but you can't just let everybody loose, there has to be documentation. Because he had this popular form, he had other concepts like a link editor when you had to link different bits of code together, symbolic addresses, and clearly programs being treated as data by other programs. So all those ideas were implied or mentioned specifically in his software discussion. He had runtime systems, I/O conversions, and some hints of macro expansion, though that's not very clearly written, so I'm not quite sure what that means. Non-numerical applications, as I already said, and artificial intelligence. So some of this may have been mentioned in the previous meeting, I don't know. The talk wouldn't be complete without talking about what happened to Turing's design. There were lots of design cycles after the project was approved. The most notorious change was the change from the interleaved instructions to optimum coding, where each instruction contains the address of its successor. Which was kind of essential to make the machine viable, but was also a pain for everybody who had to program the machine. Turing, as a pragmatist, not as a theoretician, was very frustrated by slow progress under peacetime conditions. And I'm sure there are people who are there who can tell us another version of that story.
Could I comment there?
Yeah, please do.
These kind of civil service conditions, they hadn't thought of any way to build the machine.
Yeah.
That was the fundamental problem. Not any civil service. Commercial organisations hadn't made any arrangements to build it.
Yeah. And I'm sure there was a difference from wartime, because when they decided to build the bombs or Colossus, they just did it, right? I mean, they didn't have any choice in the matter, and they just did it. So maybe peacetime civilian conditions might be fairer than civil service conditions. Anyway, as we all know, I think he left NPL for Cambridge. Things didn't work out too well in Cambridge, so he moved on to Manchester, where they had an actual computer, which is what he really wanted. The Ace family, Pilot Ace ran in May 1950, which is about 2 years after the first stored program ran in Manchester. That's the official story anyway. I'm a Manchester graduate, so I have to defend the Manchester case. The English electric juice was directly derived from Pilot Ace. About 33 juices were sold. Full-scale Ace ran in 1958, but in all fairness, it was an anachronism by then because it still had serial memory, which meant it still had optimum coding. And it wasn't, of course, the machine that Turing designed, it was based on multiple redesign. So that's the Pilot Ace in 1950. I believe the people are Olway Newman, E.A. Newman, and Wilkinson.
Joe Hallway is the one on the left.
Yeah. It should be Newman in the middle and Wilkinson to the right.
That's correct.
That was Pilot Ace somewhat later with a quite swiftly console by comparison with the previous one. I don't know who that is.
Yeah. There's another one with me there, but that isn't it.
Oh, sorry. Yeah. No, I couldn't find out any source that would tell me who that person was. But that was after it had been moved because it's in the new room.
This is in Maths building, as distinct from electronics building.
I believe that's-
Looking house.
Yeah.
Great fun putting up on the top floor with what's it called, chain.
Chain hoists. Yeah.
We all had
If you compare the two, the racks are actually very similar, but the console was sort of thrown together on a trolley in the older picture, and was a nice sort of semi-production console in the newer picture. And then of course that's as it is now upstairs in the Science Museum. I don't know who took that photo. I found it on Wikipedia, so I can only credit it to Wikipedia. So what was the telephone dial for?
if you were one-shotting through a program, well, it got a bit tedious then, so let's see if we can do it up to 10 at a time. So it was a one-shotter through a program, if you understand what I mean. Only you could do, I could do 10.
10 instructions.
Yes.
Now that's a great feature. When I was working on mini computers, I'd have loved that. One at a time was frustrating, but 10 at a time would have been very handy. Okay. What the deuce? Okay. Gordon Bell, who designed the PDP-11, used a deuce when he was a Fulbright scholar in Australia. The PDP-11 was the first widespread register-register machine. So I wrote to Bell in the 1970s, and he was still at DEC at that time. He was an on-call computer corporation by the time I wrote him, and asked him whether working on a deuce had any impact on his design for the PDP-11. This is what he replied: "Deuce certainly influenced my thinking. Some of it was negative because I was determined not to design a computer that was so difficult and tricky to program." I'm sorry, but that's what he wrote. But the fact, I took that as a comment on optimum coding. But the fact is that the unibus concept in the PDP-11, where you've got all the registers and other devices connected to a common bus, which is a two-way bus, is very reminiscent of the ACE architecture with these two buses, two serial buses going in opposite directions on the two sides. And if you look at some of the diagrams that were published when the PDP-11 architecture was first published, they look very, very similar. I only realised that relatively recently, but who knows? That's the deuce that Gordon Bell used at the University of Technology, New South Wales in Australia. So if you go back a couple, it's a much smoother console than that. Okay, ACE had cousins. It had the Mosaic, which I don't know very much. I know that it was based on version 7 of the ACE design. There was a thing called the business machine, the EMI built. There was, as far as I know, only one of them. There was a very direct knockoff of Pilot ACE, except that it had drum storage. But its design looked almost identical. Harry Husky spent a while at NPL and went back and led the design team for the Bendix G15, which was I suppose you'd call it a mini computer that sold quite a number of copies in the US mainly. Some of the people from the G15 team went to design something called the Packard Bell 250, which also sold a number of copies. I have no idea whether the company today selling PCs called Packard Bell has anything to do with that Packard Bell. One day I'll figure that out. According to Jack Copeland, the first cut of the Manchester design in 1947 owed much to the ACE design. But what they actually built as the so-called baby machine was much more like a miniature EDVAC than a miniature ACE. So I'm not sure everyone agrees with Jack's analysis of what happened there. Because Turing actually moved to Manchester after the baby had already run. So I'm not completely convinced by that story, but Jack's got quite a lot of evidence in his papers. So a more interesting topic for me, the last major topic of this talk, if you need to go soon. What happened to Turing's ideas? And the fact of the matter is, I think it's a pretty objective fact, all of these ideas resurfaced. The question is how much of that was rediscovery and how much of it was just unacknowledged reuse or transmission of what Richard Dawkins calls memes through the early computing community. So the ACE report, the original one, was maybe there were 50 or 100 copies. It was evidence that it was out of stock by 1948, because there's at least one record of NPL saying we don't have any more copies by 1948. And it basically vanished from view until it was republished during some NPL anniversary in 1972. Yes?
The Cambridge team especially, well, never been much influenced by Turing. I think that's because there wasn't any influence from Turing.
Well, that's one of the most interesting questions. Wilkes explicitly said, for example, that he didn't know anything about ACE, that he never saw the ACE report. There's some evidence to show that might be, he might be misremembering that, might have been misremembering that. Stanley Gill worked on both Pilot ACE and on ACE simultaneously. He was moving between the two places.
But most time it's actually working,
Yeah, probably.
Probably, actually.
Yeah.
1949.
Yeah. Yeah, you're right. The point is, the notion there was no communication between NPL and the Cambridge team isn't true. The notion that there was no influence is very likely true. And that in itself is sort of very interesting, because it was the very beginnings of a new technology. And I think there was an interesting sociological situation going on there, more than an interesting technical situation. In practice, of course, the Manchester team also mainly followed the Edward line with a simple sort of approach to machine design. I'm not saying Manchester built a copy of Edward, they didn't do anything like that, but they certainly didn't build a copy of ACE.
I think they got their ideas from the American machines, not
Yeah, right. But that's why the recent papers by Jack Copeland are interesting, because he says that it didn't quite happen like that. So an example that I found interesting is Booth and Booth, the book Automatic Digital Calculators by the Booth couple, 1953. It's a pretty good survey of British computing at the time. Turing is mentioned once in passing as part of the ACE team. And there is, of course, this allegation that Booth did actually visit Turing at NPL and got shouted at for his pains. But they clearly knew ACE very well, both for its electronics and its instruction set, from reading the book. And they particularly mentioned the fact that it had logical instructions as one of its distinguishing characteristics. So it's not that nobody knew about ACE in the rest of the computing community. Now let's try and go through some of his ideas. These are just the ones that we think he came up with first. Address mapping, of course, did resurface in Manchester. I'm quite prepared to believe that my former professors invented it. But it was there, it was in Manchester in 1962 in the Atlas. Everybody ended up with an instruction counter and an instruction register, probably because there's no other way to do it. So even if Turing wrote that down first, everybody else, I'm sure, reinvented it because they had to. Multiple fast registers in the CPU for both data and addressing became widespread in the 1960s, for example, in the 360. In the B-line, which appeared for the first time in Manchester in 1949, as the first index register, it was foreshadowed in a way in Turing's index-in routine, but there isn't the slightest evidence that that led to the Manchester invention of the B-line. For a start, they called it the B-line. And even the choice of name was clearly entirely local and derived from the way they were designing their machines at that time. So again, it's probably reinvention. The idea of microcode and hierarchical architecture, which is hinted at in the ACE report, was presaged also in the MIT Whirlwind, 1947, And of course, it reappeared most famously in Cambridge in 1951 and in Titan, which was the Cambridge variant of the Atlas. Whole card operations. Well, DMA gets credited to something called the NBS DISIAC in 1954. Channel I/O is credited to the IBM 709 in 1957. Again, there's not slightest evidence that the fact that Turing had whole card I/O in his mind in 1945 influenced these developments. Having a complete set of instructions, which were probably there because of cryptanalysis, well, the Manchester Mark I had logical instructions as well as arithmetic instructions. And that was relatively unusual. The IBM 701 got a shift and an AND in 1952. Probably wasn't a complete set, but at least it had that much. Again, no idea whether the fact that they were in the ACE design caused indirect influence or not. Built-in error detection and margin tests. Turing knew about that from what he saw at Bletchley Park, or possibly from what he learned from Flowers, who clearly knew that if you were going to build large-scale valve machines, you needed margin tests and error detection. Other people building computers with thermionic valves had to learn the hard way that they needed these things. Again, it's hard to know whether Turing's throwaway lines about that had any real influence. Floating point arithmetic, it appeared, he had it as a software subroutine library. He wouldn't have envisaged building floating point hardware, I don't think. It appeared as hardware in the IBM 704 in 1954. But floating point was known of conceptually since 1914, when some mathematician whose name I forget first described floating point. And it was already seen in electromechanical machines. Zuse had it in his 1938 machine. It was in the Harvard Mark II in 1944, and the Stibitz Model 5 in 1945. So putting floating point into a computer was not really, not necessarily an invention of Turing's, but we thought it was in 1975. Concept of a bootstrap loader, hard to trace, but it definitely was something like that in the IBM 701. And I'm sure they called it initial program load. That's what IBM's always called it. Modular programming in the subroutine library. That was reinvented by Grace Hopper on the UNIVAC software project. And of course it was invented by Wilkes, Wheeler and Gill in 1951 as well. That's where I'm actually quite suspicious that there was transmission of ideas, even if people didn't know it, from Teddington to Cambridge.
Can I come in there? Because it'll lose its context later. But
Sure.
Word subroutine actually was invented by the EDVAC group, and it's used at the law school lectures.
Is that right? Or what do they mean by
When when David Wheeler was designing the initial orders, he had access to the von Neumann Goldstein reports from Princeton. And that describes and uses the word subroutine and describes the whole idea of a subroutine library. So I think the idea that it might have come by Teddington is just a wouldn't hold water.
I wasn't suggesting that it came from Grace Hopper, obviously. Right, that means it wasn't known in Europe in 1945, because those reports I don't think were available. Just all that was available was all that was available was the basic one.
Well, Wilkes attended
Yeah.
law school lectures.
Yeah, that's true.
And would have heard the word
Yeah.
subroutine.
Yeah, could well be. Anyway, my point here was not to claim descendancy, simply to say where did these ideas come back from? They all did come back. The subroutine stack, that was clearly conceptually required when Algol was designed. And I didn't go back and look at the pre-Algol 60 versions of Algol, but it's probably that appeared in about 1958 in the Algol design.
I think that's by exclamation.
When?
1960.
1960. Well,
I don't know what happened before that. Dijkstra discovered the subroutine stack and introduced it in the first Algol system.
yeah, definitely. But what I meant to do, but I ran out of time, was to find the Algol 58 report. see what that said about
I
it.
don't know.
Because as far as I know, the earliest one you could get hold of today is Algol 58. But then I noticed an interesting thing, that one of the authors of the Algol report is Mike Woodger. So I'm hoping to see him in Cambridge next month, and I'll question him closely on this topic. And of course, the subroutine stack appeared in hardware in the KDF-9 in 1960, and the Burroughs B5000 in 1961, and Atlas in this case was not the first for sure, because it was only in 1962, as far as I know. Link editor, all these things. Well, autocode programming systems popped up in Manchester and Cambridge fairly quickly, and we know that Turing contributed to the Manchester software effort, including the unusable version of the autocode manual. But, you know, the first autocode solution that really worked was Tony Brooke, as I understand, in 1954, if the dates that I got were correct. You would hope that there was some transmission from Turing into that effort, but I'm not convinced. Because
I just copied Tony Brooks.
Again, Brian, his contact.
yeah,
The Turing manual was not an autocode manual.
it was a
machine stuff.
was it just the instructions for the machine? Oh, okay, sorry. Yeah.
Turing was actually extremely dismissive of programming languages. Alec Glenn, who coined the term autocode, I interviewed him. He said, when he mentioned that to Turing, he said that the shutters came down.
Yeah. There's something when you read the 1945 report, there's something in the way he describes popular format, which is the symbolic, assembly language-like stuff, that makes you think he really thought everybody should be capable of programming in binary. But he knew that, so he meant popular in the sense that the Daily Mail was popular, as opposed to the Times. So I can actually believe that. Documentation standards, which he mentioned were needed, I'm not saying he ever provided any, I'm sure he didn't. But the idea that they were needed is usually credited to Grace Hopper because of...
Can I make a quick point? On the pilot ACT, you just automatically thought of numbers in 5-bit blocks, numbers, blocks, and 31. That was how we automated it.
Yeah, I can very easily believe it. When I was programming, a really sophisticated advanced machine like a PDP-8, right, I could program it in octal because the machine was simple enough and there was little enough to remember that you could. It was easier to program it in assembler, but if I needed to program it in octal, I could. And I think as machines got more and more complex, obviously that became less and less realistic. But these days, of course, we use XML for everything. It's far superior. Anyway, what was interesting in Turing was that he knew the documentation for standards were needed before anybody had built a machine. And that I find much more interesting than whether people got the idea from it. Runtime systems obviously became universal, but I think it was remarkable that he foresaw that they would be needed. Non-numerical applications obviously became very widespread. Artificial intelligence, well, he got credit for that one along with Shannon, because the two of them did discuss AI during the war, and they both got credited for at least the concept. So, basically, I need to sum up. How much credit should he get? Well, it's clear that he was the first person to work seriously on general purpose computer design in the UK in late 1945. It was before people got together in Manchester and started working on it or anywhere else. The community of pioneers in the UK and the US was still relatively small until 1954 when Turing died. Now, we can assume that word of mouth had a significant effect and that ideas were not always properly credited. That means you can't actually find out how much transmission of ideas occurred between the various teams. There were a small enough number of people that they knew each other to a large extent. We know there was some direct influence in Manchester. We know there was very little influence from Turing in Cambridge. So I actually believe it's a rather neutral conclusion that we cannot tell today to what extent his foresights were passed on indirectly to other pioneers in the 1940s, or to what extent they were just rediscovered when their time came during the development of the industry. I finished, so we can take questions.
Brian, thank you for that. I can see a number of hands going up already. Can I ask that we use the microphone just to help people hear the questions? I think we'll start with Simon. Simon's hands up first.
We'll get it.
Thank you, Brian. Enjoyed your talk immensely. If I may, 3 small comments, then 1 question. You comment on what Jack Copeland said about Tom Kilburn's 1947 report, where he describes a storage system and, as an afterthought, as it were, gives a diagram of a complete computer. That diagram of a complete computer does perhaps show some influence of Turing's ACE report in this respect, that he doesn't, Tom Kilburn's design does not have any explicit control transfer instructions. In other words, jumps have to be programmed out by longhand. So that's first comment. Second comment on logical instructions. Very quickly at Manchester, the fundamental logical operation became the exclusive or not equivalent to function. And I remember being lectured to by Tom, who stressed that this is the one to start and finish with.
Right, I think that's provable, isn't it?
Yes.
By logic, that is necessary and sufficient.
That's right. And a third general comment, when talking about register architectures, don't forget the influence of Pegasus, end of 1955, beginning of 1956. As far as certainly Gordon Bell says, that was the first general register architecture. That was due principally, I think, to the influence of Christricci.
That makes sense, actually. Yeah.
Most interesting machine. Oh, and fourthly, sorry, there was another fourth. Floating point hardware was on the Manchester Meg in May 1954.
54.
Yeah. And now my question, if I may. Sorry.
I wouldn't mind at all if you sent me an email with those points, because I've got a chance to update the slides before the next usage.
My question, the Scientific Computing Service, which did obviously pioneering work with desk-based and mechanical, electromechanical calculators, do we know when was the first time that the SCS used an electronic stored program computer?
That's a very good question. I don't know. The trouble is, the reason I discovered that they still existed was that when I was still at CERN many years ago and was looking for a software contractor for something, they sent in a bid. I thought, good grief, I've seen that name before somewhere, and asked the guy who was in charge, is this the same company that was founded by Carpenter? And he said, yes. So I found that amazing that they were still in existence as a software house, in the 1980s. And then just recently, when I was starting to prepare this material, I looked them up to see if they still existed and discovered that scs.co.uk pointed to a furniture company, but that the administrative contact for the DNS registration was the same person that I dealt with as a software contractor 20 years ago. So I tracked him down by a great deal of Googling and discovered that, he had actually sold the company name and he sold the domain name on to this sofa manufacturing company, but that he still held SCS Limited as a private company that he owns, and I assume he uses it for some financial purpose. I would like to speculate. So I have his email address, but I don't know if he'd be able to answer questions or willing to answer questions about it. But what you ask is a very interesting question. There was certainly a software house in the 1980s, that's from personal knowledge. And there was certainly a mechanical calculating house in 1938, so somewhere in between it changed. Comrie died in about 1950. So that was why I was amazed that the company still existed. There was at least one at the front, some at the back.
Chris.
I'm quite interested in the point you made about indirect addressing as one of the key things that Turing had put in his report. Because in the main computer, out of this only 7 instruction types, 2 are unconditional jumps, 1 relative and 1 not, and both of them use indirect addressing. So, and furthermore, you've only got 32 words of memory. So in that Bailey machine, you've got to have a memory location to put the jump address and so on. And when I tackled Tom Kilburn about this, why did you do this? It seemed very extravagant to have 2 jump instructions without indirect addressing. He said, oh well, it makes subroutine return easy. But we never saw any subroutines in the Bailey machine, wasn't big enough. Kilburn implied that, oh well, that's what you do when you do when you want to do subroutine returns, you use indirect addressing. Good question whether that actually derived from anything Turing said.
That's a question I have no answer.
I'm interested that you didn't mention the fact that Turing gave some lectures in the early 1947.
Well, I did briefly mention his LMS lecture, but that was not the one you're thinking
No,
of.
it's not the ones I'm thinking of, because he just people don't know, he gave a series, I think, of about 6 or 8 lectures in early 1947. Interesting, Wilkes and Kilburn both attended the first one, possibly 2, but then thought they were so far, he was so far from the mainstream that they ceased to attend.
I can well believe it. But, I was talking about what he wrote in 1945, but I did actually meet somebody once who'd been to those lectures, and I just met him so casually, I never got his name. It didn't matter, because he said, I didn't understand a word of it. So I think there was a fairly general problem. He was called Smith, actually. I think there was a fairly general problem that, because he was of such high intelligence himself and so mathematical in his thinking, he would give lectures that he thought were perfectly clear, but nobody could understand because they just weren't given in the right terms.
Yeah, I was remaking the part not so much relative to the 45 report, but the question of Turing's influence on the projects.
No, you're right. I mean,
in the later 40s, but it seems to me rather than influence, there's a kind of a rejection almost of Turing.
Oh, there was a whole, I'm not a psychologist or a sociologist, but it's clear that he was not very good at making friends and influencing people. Definitely not.
Supplementary, since I've got that. Where do you think Turing, because I've often wondered where the word came from as a unit of computer store.
Well, as I say, the first place that Bob and I could trace it ever being written down was in the 1945 ACE report. He has this whole section somewhere, I think it might be in the LMS lecture, where he talks about papyrus rolls versus paginated books and so on. So my guess is that he was just extrapolating from that analogy, because the delay line memory is a bit of a papyrus roll, because you have to roll things through to find something.
I've often wondered if there was because you get word algebras, don't you? Don't know what they are. But I often wonder if there was a mathematical connection.
It could be, yes.
Yeah.
I carefully got an OCR version of the von Neumann report and looked for the word
Yeah.
And it occurs something like 3 times, but always in the phrase, in other words, or the other words. So it's absolutely not in the von Neumann report.
And it's used throughout the EXAC materials. So,
It may have.
it just seems unlikely that it would diffuse.
It may have become common currency by the time of the Moore School lectures. Who knows? If everybody had been carrying a tape recorder all the time, we'd have found that.
I'll come back, David.
I'm glad you mentioned CERN, because something from your lecture made me think of Tim Berners-Lee, in that Turing seems to have collected some ideas and put it all together, rather like Tim Berners-Lee did when he did the World Wide Web. In other words, quite a lot of the stuff was already there, but he had the foresight to pull it together. And it just seemed there was sort of some commonality between what they did. Well, they both invented extra bits as well.
Well, the big difference, though, is that Tim is very good at making friends and influencing people. And, you know, I was sitting in my office one day, and Tim came in and said to me, "Are you logged into Prime," which was our main Unix server at the time? And I said, "Yes." He said, "Type what?" I said, "What? Type what?" He was very excited. He was saying, "Type www." So I typed www, and up came the line mode web browser. So I was, you know, an alpha test customer. And, you know, 2 years later, he came in and asked me the same question, except by that time we were using X Windows, and he said, "Bring up Mosaic," right? Because that was the week Mosaic was released. So Tim could do this. He could go and inflect people with his ideas. And I don't think Turing had that gift. I think that's a difference.
As everybody knows, I'm an avowed fan of Cambridge. And you are the second person this year I've listened to give a lecture on Turing who has dismissed Cambridge as far as possible. And I will mention that Cambridge built the world's first computer to go into stored program computer to go into regular service. You mentioned in your talk how Turing went back to Cambridge for a short time after NPL, but you said something about he had an unfortunate experience. What was that?
As far as I know, you know, it emerged then that, you know, Turing and Wilkes basically couldn't communicate with each other effectively.
I understand he made no attempt to actually talk to Wilkes.
Well, that may well have been his way of
Yeah,
communicating.
Wilkes claims that he is innocent.
Yeah.
Unfortunately, he can't pretend that.
No, I'm not attacking him.
But it's extraordinary indeed how those who are pro-Turing, and I respect that, I mean, he's an incredible man he was, there's no doubt about it, somehow likes to skip over Cambridge. Because somehow you have a difficulty with Cambridge.
I don't actually. I mean,
well, you sounded as though.
Okay, I apologise for that because, you know, I think EdSac was tremendously important and Leo was tremendously important. And by the way, when I was an undergraduate, walking across the Downing site, I found myself kicking bits of EdSac 2 out of the way because that was fairly soon after.
By the way, some errors in your slides, I'll put you right on.
Send email, please do. So I would like to perfect them. And by the way, the only person I've ever had a formal lecture about computing from as a student was Wilkes's lectures on numerical analysis.
Which were well known not to be very good.
The numerical analysis part was horrible. He hated it and the students hated it. But he gave a few lectures on Titan and Time autocode, which were wonderful.
I'm learned a great deal this afternoon about Turing's contribution, which went a lot further than I'd imagined. But I'd still like to repeat a remark I made previous meeting here, that the whole future of computing would have been better if Turing had never existed. Because NPL, for instance, would have taken the Cambridge design, the one address machine, backed by English Electric, then large industrial and numerical power behind that, and that would have been a much better way to go on the single address machine than on the very involved one that then so many of us on rather a long dead end have started, even after what I've heard this evening.
Stunned silence.
You mentioned earlier on use of Meccano for making differential analyzers, and most people here know that actually happened. About 10 years ago, a letter appeared in the back of New Scientist, I think it was, saying, has anyone ever used Meccano for a serious purpose? And that letter was written by Gary T. of Auckland University, so I guess you know him.
Yeah.
I wrote back saying, yes, there is such a Meccano differential analyzer in the Museum of Transport and Technology at Western Springs, Auckland, which I guess you also know. I would love to know if that differential analyzer was subsequently found, because I think it was, when I went to the museum about 4 years ago, it was a theme park compared to what it was 30 years ago.
The expert on that in this room is sitting right next to you.
Martin.
Not only is it there, but the man who installed it demonstrates it from it drew a circle.
Have a photo of it somewhere. Thanks a lot.
I'll come back.
I accept it.
Just a couple of quick comments. In terms of influence, I came across a 1947 research grant made by Andrew Booth, which says he has, talking about Turing as one of the current workers in the field, and he says that he has a rather old report, I suspect almost beyond doubt, a copy of the 1945 report, and he said, and a few more recent conversations, and that he also elsewhere commented in 1952 on the reliability of Turing's design, the hardware, but he does make the, he also, but he makes the comment about the 1940, in his 47, that it seems principally to be about a logical design rather than for numerical calculation, talking about Turing's design. The other comment I would make is in respect of Hartree's book, which from 1948 and then the second edition of 49, which again makes very brief reference to both ACE, I think it's a couple of references to ACE, and a couple of references to Turing, both of them in the context of extensions to diagramming techniques, which does suggest that Hartree's assessment was that there was not a great deal circulating in the UK from Turing for other groups to utilise in their thinking.
And it gets back to the point, I think, that his design was, and you said it as well, actually going off in a slightly strange direction. Right?
Well, actually, while I've got the microphone, to my mind, I don't think Colossus has any facilities for marginal checking. In fact, such as the power supplies in Colossus, looking for Chris, who's hiding away, it would be actually very difficult to actually adjust the HC supply. That doesn't mean to say that Tommy Flowers wasn't aware that it might not necessarily be a good thing, but certainly Colossus has no facility for marginal checking, or marginal testing. Sir.
Thank you. Talking of Turing and Cambridge, I was in Cambridge a fortnight or so ago, showing a visitor around. We went into the Brown Church there, where they're showing a video thing showing history, etc. of Cambridge. And there was a section on Cambridge and scientists, which mentions Newton and Rutherford and various other people. But not only was there no mention of Turing, there was no mention of Babbage either, which very much surprised me.
Too many Cambridge scientists.
Incidentally, my wife was a pleasure principal of poetry in the mathematics division at the time that Turing was there. My late wife, I should say. She had a very low opinion of him, but this was probably due to his not being very communicative with people.
Yeah, I suspect so. But you get the impression that some people were very much liked him, once they accepted the way he was.
Any further comments or questions for the meeting? Okay, Kevin. Right. Well, can I start, Brian, by thanking you for a most interesting lecture this afternoon, and we thank you for taking the time to come on your stay in the UK this year. Can I also say, as I said at the beginning, this is our final meeting of the session. The good news that I can share with you, since my usual role is not as chairman, and I'm delighted to see Rachel arrived shortly after Brian started his lecture, that in my role as the programme secretary, I'm delighted to announce that we have a programme till Christmas, that an as yet unnamed Cambridge academic has agreed, subject to checking his diary, that there will also be a lecture in January. March, April and May are committed, so we have an almost complete programme for next year. The running order for the autumn, I'll just read to you, and it will be on the website shortly. The September 20th meeting, which will be our first, I'm delighted to say that the chair of the Conservation Society, Rachel Burnett, will be speaking on adapting and innovating the development of IT law, which is an area of expertise of hers. The October meeting will include the AGM and will start at 2 o'clock, or if you prefer to avoid AGMs, at 2:30. And we have an interesting mixture of speakers, one from the National Archive, one from British Library, and David Holdsworth from the Conservation Society. And the title there is Conserving the Past for the Future. And the three speakers will address the problems of, first of all, conserving data and the contents of websites, and then the conservation of the software in order to animate the data and websites. So an interesting afternoon there, I think, potentially. November, we have John Hitchins, who is an expert on the history of machine translation. And that, I think, promises to be an interesting afternoon as well. And the December Christmas meeting will feature the usual suspects and a lot of old film, we hope. So that's the programme till Christmas. In the new year, we'll be hopefully looking at the history of Atlas, information retrieval. Doran will say a bit about Babbage and an analytical engine, and we will also hear from the team building the EDSAC replica. So the year ahead promises, I hope, to be an interesting one, covering all sorts of new ground, and I look forward to seeing you all. I wish you all a very happy summer, and the next meeting, as I say, will be on September 20th, and Alan will shortly have the programme for me to go on the new website. So can I invite you now to once again thank Brian for a fascinating afternoon, and Brian, thank you very much indeed. We hope you enjoy your summer in the UK and a safe journey back to New Zealand in due course.